Good afternoon, everyone. Welcome to the fourth session of our show and tells for round 2 alpha. Next slide, please. So my name is Ellen Webmore and I'm an innovation lead on the SIF. Next slide, please. This afternoon, we'll be showcasing 5 projects which are centered around the theme of delivering a smart, stable and flexible energy system. So projects in this alpha phase have just completed a 6-month program of work, with those projects being awarded up to £500,000 in funding to complete that work. So this phase is the middle phase in our discovery alpha and beta approach. So this is where projects are refining their problem statement and setting a robust foundation of research to prime them for a potential demonstration project should it be necessary. So before we kick off with the projects, I just wanted to give a bit of background about the SIF and its strategic vision. So Innovate UK deliver the SIF on behalf of Ofgem with a vision and purpose at the forefront of that delivery. So the delivery is the vision is to deliver net zero at the lowest cost to consumer and make the UK the best place to grow and scale an energy business in the world is the aim, and our purpose is to do this for the benefit of people, the planet and businesses. Next slide, please. So yeah, for a bit about the SIF, it is an innovation incentive set up as part of Ofgem's price control, meaning that it is funded by the consumer through their bills. The program is delivered over the course of the price control, which is 5 years, with 450 million in funding to be delivered over that period. The SIF has replaced the Networks Innovation Competition, which was its predecessor, if some of you may remember it. And we've got an early indication of benefits here for you. Next slide, please. So for our agenda for this afternoon, we'll be hearing from 5 projects which are in the realm of delivering a smart, stable and flexible energy system, which is our theme for this afternoon. So just for a bit of background, as we transition towards net zero and away from fossil fuels, we want to ensure that the networks evolve to make way for a system that's flexible and can still balance and stabilize our system, but one that doesn't draw on fossil fuels to do this. So this is a major challenge as we move towards being more reliant on variable and distributed forms of generation. And this afternoon, we'll be hearing from 5 different projects who in different ways are looking at tackling this theme and or components of that theme. So without further ado, we are ready to go with HyNTS hybrid storage.
Hi, good morning, everyone. I'm Ellie. Sorry, can everyone hear me all right? Sorry, I haven't used Zoom very often.
Yes, I can hear you.
Perfect. Yeah, just want to recheck before I start speaking. Yeah, so good afternoon, everyone. I'm Ellie. I'm an innovation specialist from innovation team. Yeah, so today I will present on the SIF hybrid storage project alongside with the project partner who've been working very closely within the project as well. So in short, this project will investigate the use of hybrid storage system to provide a safe and efficient storage of hydrogen for our gas turbine operation. Yeah, so just to paint a picture on that, across the national gas transmission system, there is many different types of asset and equipment present at the moment. They play quite a great role on the safe and reliable operation of our gas transmission network. So the national transmission system are currently using the compressor or the compression to manage the pressure and flow within our pipeline in order to make sure that the gas demand can be met. The majority of the compressor on the NTS are driven by gas turbine, which are fueled by our existing natural gas within the NTS or within the pipeline. And these assets have produced quite a significant emission regarding to burning burning the methane, and it's also generate the wet heat which are currently lost into the atmosphere at the moment. So within our previous work, we have had a number of the projects looking at the potential to have the hydrogen generated at the site and then fuel our gas turbine by using the hydrogen. Yeah, and we have sort of identified within the previous project that the storage is going to be a key element in order to keep the site and the capex of our electrolyzer unit as cost effective as possible. Another most important economic element is coma regulation, which is a regulation that prevents and mitigates the effect of major accidents involving the dangerous substance that can cause the serious damage or harm the people or even the environment alongside the location. And obviously that is going to include hydrogen, because hydrogen is the lightest compound in the entire world. Yeah. So within the table at the right hand side, you can see the limitation of the coma regulation. Yeah. And as a result, we are looking at the hybrid storage system within the alpha phase of the study to explore the potential to use the hybrid storage and also avoiding that 5-ton hydrogen limitation of our existing site. Next slide, please. Yeah, and just to build another bit of the picture on why do we need to use hydrogen and why storage is the vital element. So most of the gas turbine in our network can be repurposed to hydrogen. There is a project which is a part of SIF Beta Round 2 that is currently conducting the demonstration of our existing gas compressor at the moment, and proving that our compression system can be repurposed for hydrogen, which is the future grid compression project. And also the gas turbine are not running constantly. It is depending on the fluctuation of the demand for gas, and also and also the other element within the operation as well. And as a result, we need storage. We need hydrogen storage facility in order to provide flexibility and make sure that our supply of hydrogen will be able to tackle with the instant demand of the gas. Yeah. Next slide, please. So storage and release of hydrogen within the relevant time scale is going to be vital in order to ensure that there is a consistent energy source and improve resilience of the network. Yeah, and that is why we are having a look at the study of this system. Yeah. So, for example, the compressed gas storage is already a method that is being utilized widely today within the green hydrogen production. However, for our operation, the site requirement and the safety of the system is going to be limited, and we need to look for the alternative technologies such as solid-state hydrogen storage to provide the benefit of the solid storage density and also safety. But I mean, I think within the discovery phase of the project, we have sort of proved that the solid-state storage couldn't supply hydrogen for our operation alone, and that is due to quite a low release rate of the system. We can't tackle with the requirement and also the demand. And as a result, this project, we would like to have a look at if we are hybriding the solid-state hydrogen storage system alongside with gaseous hydrogen storage system, how can the system provide safe and efficient storage for our of hydrogen for gas turbine? And just a bit of a quick explanation on the solid-state storage. So because hydrogen is going to be react directly with the storage material itself, yeah, that is why the solid-state hydrogen storage technology is actually offering the benefit on the potential to avoid the coma regulation, just because technically the component that being stored at the location is not hydrogen. Yeah. So next slide, please. Yeah, so just to introduce on the project plan that we have conducted in the alpha phase and also the project partners. So we have been working alongside with MTC, Hydrogen2Go, as well as Hydrogenous and UKPN. Yeah, so I've been working very closely to looking at the energy modeling of this system, the techno-economic analysis by utilizing HyNTS of the system, as well as conducting the system demonstration design and define what direction is going to look like after the alpha phase of the study. Next slide, please. Yeah, so within the alpha phase of the study, we have had a look at one of the compressor station location, and we get the understanding that the peak fuel consumption of the site is going to be 45 megawatt capacity. Yeah, and more importantly, we also have found that there is a selection of the system configuration in order to using the hybrid storage within our operation. And we also have proof that the different storage material from Hydrogen2Go technology could actually support the different deployment of hybrid storage system and also meeting the requirement of the gas turbine. More importantly, the energy model have shown that if we are blending 25% of hydrogen into our gas turbine, we will less likely to need any additional hydrogen supply from either through the vent or the alternative hydrogen producer. However, if we actually going to blend 100% of hydrogen into the gas turbine, there is more likely that we will need additional capacity or additional hydrogen supply from somewhere else. More importantly, so within the location that we have a look at the study, we have highlighted the associated equipment of the system is going to fit within the highlight or within the space available at the location. We are also looking at the hazardous area zone as well, and the findings have shown that the system can be kept away from the site boundary and wouldn't affect the hazard within the location majorly. Next slide, please. Yeah, and the next part is going to be presented by Andrew Perkins from MTC.
Hello all. Yeah, working on the alpha project, the alpha phase, the MTC had deliverables that spanned a range of project work packages. The first of these being benchmarking review. And for this deliverable, we researched global hydrogen projects that had hydrogen production and storage elements to them. We made comparisons based on a set of criteria, such as the technology readiness level, commercial readiness level, levelized cost of hydrogen, time to market release, and hydrogen output. We concluded that the proposed SIF hybrid storage solution was comparable, but with the incorporation of newer technology, such as the solid state storage and the solid oxide electrolyser. Following the benchmarking review, we moved on to the additional storage solutions deliverable, where we compared a variety of storage options that could sit alongside the solid state storage as part of the hybrid storage system. We compared a variety of solutions such as compressed gas, liquid hydrogen, and a variety of other material-based storage solutions. We liaised with various suppliers and determined a list of categories for comparison and benchmarked the solutions against one another. We concluded that the compressed gas is the most suitable option as it is of relatively low cost. Following on from the additional storage solutions, the team produced the energy model deliverable, creating a programmed model that could simulate how the pieces of equipment could generate, store, and empty of hydrogen to supply the gas turbine with fuel. To understand how the model would behave, past turbine runtime data was analysed and broken down into 6 scenarios that would most challenge the capacity of the hybrid system. Following the running of the scenario simulations with electrolyser size and storage capacity selected, it was apparent that the system could provide the turbine with 100% hydrogen to enable the turbine to run in idle and a minimum governance state, To satisfy the higher fuel consumptions with the proposed system, a blend of natural gas and hydrogen would be required. The next slide, please. An output of the system design deliverable was a high-level piping and instrumentation diagram that incorporates the main system elements. This P&ID diagram does not represent a final detailed design, but is to be used to inform the process engineer at beta phase of the concepts developed during alpha phase. The top row shows the electrolyser producing hydrogen, then compression to ensure the hydrogen is at the required pressure for supply to the turbine fueling system. Then a second stage of compression and a gaseous storage element to the system that complements the solid state storage to achieve the required flow rate. Followed by a pressure reduction station to bring this pressure of the outputted hydrogen from the gaseous storage back down to that required by the turbine fueling system. Below the top row are 5 boxes depicting the solid state storage. This system configuration is versatile and can meet the fuel demands of the turbine when supplied with a 25% hydrogen and natural gas blend. The hydrogen produced by the electrolyser can flow in and out of the gaseous storage and the solid state storage, and can also flow directly to the mixing skid. I will now pass back to Ellie. Thank you.
Thank you, Andrew. That's really, very insightful. Yeah, so next going to be a presentation from Luke from Hydrogen to Go.
Great, thanks very much, Ellie. Yes, next slide, please. Yes, so H2Go, so we basically cover 2 sort of development streams as part of this proposed SIF proposal. So we do solid state storage, which kind of Ellie's described, as well as AI optimization of the sort of entire value chain, hydrogen value chain. And in this case, we've applied it specifically to the turbine and gas compressor use case. In terms of the solid state storage, yes, like Ellie said, it's we store it in materials. We pack this inside a shipping container, then you have this plug and play shipping container. So it's gaseous hydrogen in, store it for a period of time, heat it up, and then the hydrogen comes out. It's low pressure, it's the same density of cryogenic liquid, but all at room storage at room temperature. The hydrogen optimization platform that we use, it's using data from the site, which we then can do better informed decision making. It means that we can optimize the size of different assets at the site for the use case, but also in terms of real-time control in terms of when to turn things on and off. Next slide, please. And just passing over to Josh, who will cover sort of the software piece side of things.
Great, thank you, Luke. And yeah, as Luke just alluded to then, what we're doing on the optimization side of things is really looking at building on the great work that the team at MTC did to look at how we optimize the infrastructure sizing of the system when we scale this up to multiple sites in the NTS in the beta stage and beyond. And the objectives that we're looking to optimize is to maximize the total amount of carbon abatement while also minimizing the levelized cost of hydrogen. And you can think of these two as a trade-off in the sense of, given that we have to decarbonize, how can we do this as cost effectively as possible so that minimal costs are passed on to the end consumer? And as you can see here, there's a variety of key infrastructure sizing decisions that we have to make. And one of the key things is the balance between compressed gas storage, which is limited in capacity due to the COMA regulations, and then additional solid state storage. And we perform this optimization using an iterative procedure that uses AI to learn from previous simulations and thereby efficiently identify the optimal configuration of the system. Next slide, please. The key result of this is a recommendation of infrastructure sizing that provides the optimal trade-off between our 2 objectives. To remember, one of them is cost effectiveness in terms of levelized cost, and the other one is the amount of carbon abatement. The plot here on the left, each dot shows an individual trial of a particular configuration of the system that was run, and the blue dots represent the optimal trials, which represent the efficient configuration of the system, which achieves a good trade-off between these 2 objectives. On the top there, you can see we've picked 2 points along this efficient curve, which represent one preference towards lower cost and one preference towards higher decarbonization. Importantly, in both cases, we see benefit in adding additional solid-state storage capacity in addition to the maximum compressed storage capacity due to the coma limit. And the plot on the right here shows how in either of these configurations, the solid-state storage enables us to achieve a boost in carbon abatement of somewhere between 9 and 32%, depending on our preference for cost effectiveness. Next slide, please. Back to you, Luke. Thank you.
Yeah, thanks very much, Josh. Yeah, so part of this project, so we do have developed IP to enhance the flow rate from these materials. So these materials aren't new, they've been known in the industry for a while, but there's been a limit to how quickly you can scale them up and use them in real world scenarios because of the limit at which you can release that hydrogen. And this is mostly down to heat transfer. Our existing performance materials, we were sort of getting delivery pressures up to 3 bar, which is good for some use cases like fuel cells and other heating appliances. But for this application of the turbine, we really needed to get up to about 16 bar. And also the higher flow rate. So we did enhance the flow rates initially, but this use case, you need especially high flow rates. And that's why we have this combination of solid state and gaseous storage to meet those additional flow rates as well. So, but as part of this project, we did some lab testing of each modular reactors, which you can see on the left-hand side, which we stack inside the shipping container. And we managed to increase the pressure output 5x and double the flow rate twice, so 2x. So it was a sort of really successful project for us. So now we've done this sort of thorough lab scale testing. As part of this project, we also enhanced the design of our shipping container, which is basically on the left-hand side there. And you essentially have all your balance of plant in there, and you can, if you need to increase storage, you can sort of modularly increase the amount at your site by installing more and more of these shipping containers. So to the left, yeah, so for the left-hand side image, that's storing about 200 kilograms of hydrogen. So you can imagine if you need to store a ton of storage at your site, you'd have 5 of these containers. Next slide, please. So yeah, this is just sort of summarizing some of the outputs. We managed to double the flow rate, increase the output pressure by 5x, which meant that it was viable in this use case of the hydrogen, the turbine use case. And I think we've successfully shown that we can use a solid state storage to mitigate against the coma regulations, which are costly, but also enhances safety at the site and surrounding the site as well. So you're already storing hydrogen until you need it, for instance. The use of the AI basically managed to find a more optimal configuration, which meant that there's better use of proceeds and funds to build these sites. But also it's designed for the live operation. So as part of the next beta stage, we would be looking at the control of the system as well. Yeah, I will stop there and hand back to Ellie.
Thank you so much, Luke. Next slide, please. Yeah, so the next element is on the benefit of the hybrid storage system. So regarding to the financial perspective, by using this system, the operating of the network by using the network gas could be optimized and also reduce the utilizing locally produced energy, renewable energy source as well, because we are going to producing the green hydrogen on site. And additionally, there could be a financial intensive to reduce our emission within our operation of the network, which is we are planning to implement this in 2030s onward. Yeah, and regarding to the cost saving from our operation, that will obviously reflecting to the cost saving for the consumers' energy bill, as well as the user of the network service as well. Regarding to the carbon saving, so that is going to be the direct carbon saving per year, against our current business as usual operation, regarding to using hydrogen and also using hybrid storage to increase flexibility of the system. That is also going to be the improving in the efficiency of storage mechanism that will also consequently reducing the overall impact of the energy system as well. And more importantly, it is new to market. So this solution is relatively new to the market. It hasn't been utilized anywhere else before. Yeah. So, I mean, as part of this study, we also engage quite closely with the industrial and transport hydrogen user because we are quite keen to understand, besides using this system for our operation or for our emission reduction, what sort of the wider application of this innovation, and how could this being applied to either hydrogen user, hydrogen supply, or wherever hydrogen is, in order to provide a flexibility in the wider energy system and hydrogen value chain. Next slide, please. So what's gonna happen next after the alpha phase of the study? So under the next phase of the study, we are planning to finalize the full system design and cost, and also decide the integration of the system for our selected testing site for the next phase as well. We are planning to conduct the demonstration of the hybrid storage system for our NGT operation, and also for the wider application, as I have mentioned previously as well. So we are seeing the demonstration of this system not only to bring the benefit into our operation. We would like to explore, is there any chance that we could bring together the industrial or transport user, and then also using this testing site to prove the applicability of the hybrid storage system as well. And as a result, we would like to engage with either hydrogen user or supplier and explore what is the wider collaboration opportunity that we can have together. And obviously, after the demonstration demonstration process, we are planning to roll out the system. So we would like to see how does the system going to look like if we actually roll out this solution across the NTS network or across the asset in the UK. So we will continue to understand our business case and see how it will look like if you have a full rollout to the network. And yeah, I think that is pretty much everything that I would like to cover today from the hybrid storage perspective. Thank you so much for your listening, and I hope you find it useful. Yeah, happy to answer any question you may have.
Thanks for that. I see we have got a couple of questions in the chat, which have already been answered, which is very efficient. If there is no other questions, we'll leave that open for a little bit. And yeah, we'll thank you all for your presentation. Good luck with the beta phase, and move on to the next presentation, which is from SIF Blade.
Hi. Are we okay to move to our slide? Fab, thank you. So hi everyone, welcome to our show and tell presentation on the SIF Blade alpha phase. I'd like to quickly introduce a few members of the team. So my name is Kira, and I work for Carbon Trust. We also have Augusti on the call, who works both for Scottish Power Energy Networks Transmission, and we have Gordon on the call, who works for TNEI, and Rob, my colleague at Carbon Trust as well. So they will all be presenting alongside me in a moment. Are we okay to go to the next slide? Thank you. So what is SIF Blade about? The SIF Blade project has identified the challenge of using offshore wind to provide grid restoration or black start services. So why do we need to explore offshore wind as an alternative to the current technologies used? Well, currently in the UK, we're undergoing a network-wide retiring of carbon-intensive black start assets, which traditionally provide these services to the onshore network. In addition to this, there are new requirements for energy system restoration being defined, and there is huge growth in offshore wind sector and in grid forming technologies and their technology readiness levels, so they're coming to market soon. And there is a lack of clear guidance on how we can utilize offshore wind to provide these services. So what needs to be demonstrated or developed? Well, the technical feasibility of new black start technologies needs to be proven. The commercial viability for service providers needs to be defined, and the procedural and regulatory clarity needs to be sought to enable providers to participate in the market. And so why is this currently funded by the SIF? Well, there are a number of positive outcomes to the GB consumer if offshore wind was to start providing these services. So it will ensure a robust net zero energy system. It will reduce emissions for consumers and help us reach our 2050 targets. And it will provide competitive alternatives for black start services, which could provide savings to the consumer as well. So hopefully financial savings across the board. Do you mind going to the next slide, please? So in SIF BLADE, we have a very large consortium. I introduced a couple of my colleagues there, but as you can see, it's quite broad. The consortium consists of onshore networks, offshore network designers, transmission system operators, offshore wind developers, research institutions, and technology suppliers. And the breadth of this consortium has been essential for the understanding and defining the offshore wind's capability and offering to the GB network. And a very key part of this project is bringing everyone together to solve the problem as a very large group. Next slide, please. So what have we looked at in our alpha phase activities? Well, work package 1 has looked at the technical assessment of the onshore system restoration from offshore wind. Our work package 2 looked at both the business case assessment and undertook an offshore and OFTO regime review. Our work package 3 looked at the technical assessment of the onshore system restoration from a coordinated offshore network. Our work package 4 has scoped a beta phase, so looking at what work still needs to be done to ensure this technology can get to business as usual. And our work package 5 has just consisted of general project management. So we will talk about some of our work package 1's findings now. If you don't mind moving to the next slide. Augusti?
Yeah, so good afternoon, everyone. My name is Augusti here. And what I would like to discuss with you is a little bit the technical or the results of this technical work package 1. That probably some of you might argue that if you look at the network and electric network and you look at the wind farms, you might argue that, well, we have a network and we have wind farms already available and we have done Black Star and we have restoration plans already in place. But what we have to understand here and why this is a sweet spot is that basically the way that Black Star is done from offshore wind is substantially different. One, from the network point of view, because we are looking at different restoration paths. We are looking at different routes that electricity should go, and these are not designed for restoration. And the other thing is that wind farms are not designed for this. So what we believe is that doing some enhancements, this might be possible, but this is, let's say, why we are applying for SIF, because we believe that doing a little bit, we can deliver a lot for the consumers. So what we did in this project is we look at the central Scotland area, we look around the central belt, Scottish Power Energy Networks area, and we look at the wind farms that they are coming in the future. And what we saw is that doing very little, we can enable Black Star. And just to make it absolutely clear, here when we talk about Black Star from offshore wind, people might say availability. I said, well, gas always is there. But what we have to understand is that, well, as we saw last year, probably gas is not always there. And apart from that, we have a lot of offshore wind being installed these days in Britain. In fact, it's going to be the first way to generate electricity. So the idea there is that we look at this, and what we saw is that if these future wind turbines in Scotland, we have wind speeds average or even below average, we can restore the electric power network according to the new government requirements of 60% of the load in 24 hours and 100% in 3 days. And to do that, what we have done is several feasibility scenarios. What we have done is we have looked at different technologies, for example, self-starting wind turbines, and also a start from a battery onshore. And what we have seen is that both the scenarios are feasible and viable. And what we have seen, what we have been doing for the extras that we need to add, for the extra technologies and extra bits that we need to add, we have been discussing with OEMs and government and different providers to understand if this technology is going to be there. And apparently, I would argue that yes. And this is a nice context for beta. We still have further work to de-risk, let's say, understand better the technology that we should order, understand better if the restoration path that we have chosen are good enough. But so far, from the alpha point of view, it seems that we can do it. And next slide.
Fab. So the OFTO regime review. So the OFTO regime review looked at the current regulatory environment and OFTO regime in relation to offshore wind providing these black start services. In this work, no significant regulatory gaps were identified. However, new regulations are being introduced around the time of the beta phase, and therefore we plan on monitoring this in a next phase of the project. No prohibitive roadblocks in the OFTO regime are expected to undermine the offshore wind market participation. But again, we do plan on monitoring this in a future phase. And the work undertaken in the project did identify that market requirements need to be defined or updated. And this is part of the work that we do propose to do in the next phase. So just making sure that we are accounting for availability, etc. Overall, the outcomes of this work package were quite positive and no major roadblocks have been identified. However, this is only part of this work package. The second part of this work package is the cost benefits assessment, which Gordon will be presenting in the next slide.
Good afternoon, everyone. So as Kira says, we've been modelling the sort of GB-wide cost benefit case for the concept. So in contrast to the work Augusti presented, which was very technically detailed, focusing on a specific part of network, we've been looking a little bit more higher level, but trying to extrapolate across the entire system. So I won't go through all the ins and outs of exactly how we've done that modelling, but I'll just talk through I guess the key takeaways that we're getting from that. So the main thing is that under some of the future energy scenarios that we've looked at, the ability to have offshore wind contributing to system restoration is essentially required. Without that capability, some of the scenarios seem like they won't be able to achieve the restoration targets and the standard that exists. And that's kind of a phenomenon that we see in the kind of late 2030s into the 2040s, particularly when there's lots of renewable technology and a very significant changes to the composition of the energy system. Now, of course, the capabilities that we are talking about and requiring don't currently exist, which is what we're kind of finding elsewhere in the project. So our conclusion, therefore, is that we either need to develop that capability in the BLADE project and at quite a large scale, because in some of these scenarios we're testing, we end up using a lot of offshore wind in order to provide this capability. The counterfactual is essentially to have dedicated restoration generators, which, if we're going to be consistent with net zero and so on, would have to be some kind of low carbon thermal generation technologies which don't currently exist. It would be expensive anyway, but particularly expensive if they're sitting there just in order to provide system restoration. So essentially our key takeaway is that BLADE seems to be a relatively low regret option in order to ensure that capability for the offshore wind fleet is there in case we need it later on in the 2030s and on. Thanks. Is that back to you, Kira?
No, across to Augusti again.
Back to Augusti, sorry.
Yeah. So, yeah. So, now we are going back at the technical part. So basically what we saw from the feasibility study, from the technology point of view, we saw that BLADE is achievable and is something that, let's say, looks promising for the demonstrator and can become a product. Also, we saw that, what Gordon presented in terms of the economic feasibility. But one thing that we have to keep in mind is that here you can see in the map that in 10, 15, 20, 25 years, here you can see these yellow squares. So these are future offshore wind farms. So basically, it's likely that as a result of BLADE, we are going to have a piece of regulation, a market, and a piece of technology developed. One of the things that we have done is look at the future. So this is how the future is going to look like according to National Grid. And all these green squares are offshore wind farms, that some of them, they are going to be using a different technology that is called HVDC, that is using DC technology instead of AC. And what we have done in Work Package 3 is look at the feasibility to unlock these wind farms that they are going to be installed in the mid to long term in order to provide restoration services. And what we believe is that as we are doing BLADE and we have these wind farms planned, one of the things that we have to do is start to write the specifications, considering that these wind farms might be able to provide, and this is one of the findings from this work package. We can enable even further offshore wind farm to provide restoration. And that's it. Next slide.
Okay, thanks, Augusti. So we're going to go now and talk a bit about what we plan to do for the beta phase. So maybe this slide just sets out the background. As Gordon mentioned, there is a urgency identified for offshore wind farms to provide these restoration services to get these the necessary scale. We really need to start seeing the wind farms being built by 2028, 2029, 2030 onwards with this capability. We've also found, I guess, maybe a point that was maybe skated over, that retrofit of this technology is really difficult. So basically it needs to go in at the point at which it's being specified and designed and built. And we know that there's a huge pipeline, I think 50 gigawatts by 2030, more by 2040. So we need to get this technology in. However, significant uncertainties around technical requirements, TRL of some of the technologies, market requirements, commercial arrangements, as were pointed out on the previous few slides, do exist, and we need to address those. And fundamentally, I think Augusti alluded to this as well, but we really need to change the mindset of restoration into more of an integrated whole system approach to achieve net zero compatible restoration, rather than relying on, one or two or a small number of large thermal generators. So I guess the current way the market is run is set out on the left-hand side, and I think SIF Blade's approach to provide evidence is set on the right-hand side. So on the left-hand side, the market's very much set by the ESO. They communicate with TOs during a restoration, and also to ensure TOs are ready for restoration. And they also set market incentives and market requirements to generators, and in this case, we're looking obviously at offshore wind farms and offshore wind farm developers. Those offshore wind farm developers pass those requirements on through to their OEMs, such as battery OEMs or turbine suppliers. I think that approach can work in terms of the large thermal generators that are well known and well understood in the restoration market. However, at the current stage, we don't think this is the correct approach in terms of encouraging new participation from new technologies. So what we want to do is on the right-hand side, which is really starting from the bottom up and having connecting some of the dots between the transmission system owners, the TOs, the offshore wind farm developers, and the OEMs. It's really those three, those boxes, those stakeholders who are going to be owning and developing the technology that's going to enable this integrated whole system approach. And as Kira mentioned in the first slide, having this large consortium is essential to achieving that. And what we'll be doing by the end of the project is feeding that evidence up towards the ESO, such that they can understand what the industry is capable of from a technical perspective, and hence set suitable market requirements to incentivize future generators to install this technology. Next slide, please. This is an overview of the approach for the beta phase. I think I'll actually start this slide at the bottom. Augusti mentioned looking at the Scottish Central Belt and the offshore future offshore connection, future offshore network location. You can see those pointed out at wind farm 1 and 3. We're also going to look at another wind farm around the Peterhead area. So we're looking at 3 separate locations, 2 actual locations and 1 future location. And these all have been selected because of their different restoration requirements. So, around the Branxton area, there's a lack of restoration from any source. Around Peterhead, there is some hydro possible, and wind would have a different role in that restoration scenario. And then wind farm 3, looking at the offshore coordinated network and the DC coordinated network. Again, different restoration requirements on those wind farms. So we think if we can cover these 3 areas, we'll be looking at quite representative scenarios that can be rolled out to all locations, GB and also internationally. So how are we going to study these locations? If we move back to the top, so it's looking at work package 1, we'll be doing site-specific detailed feasibility scenarios, detailed feasibility studies, basically assessing various wind farm options, technology options, and selecting the optimal ones. So we'll be looking at the various restoration methodologies and the grid requirements for those restoration methodologies. We'll be developing suitable solutions. That's the wind farm, that's the at the grid level. It's also all the components like the turbines and the batteries themselves, and also the overarching controller systems required. And then we'll be assessing those options through technical feasibility studies, looking at the costs, looking at the savings, looking at any regulatory issues and any other risks identified. What we'll do then is go through a stage gate into work package 2. We'll be selecting the preferred options, and we'll be doing a much more detailed study de-risking, verification, and demonstration of those technologies. That will be the second half of the project. Both of Work Package 1 and Work Package 2 will feed into the commercialization work stream. This will actually be conducted throughout the project, but here it's listed kind of towards the end. But essentially, this is really to support that rapid, full-scale, nationwide and international deployment of this technology. So we'll be looking to disseminate to National Grid ESO and also international TSOs who are involved with the project in terms of what offshore wind can provide. I'll be looking at providing standard technical specifications to transmission owners, to OEMs, and to offshore wind farm developers, such that they can uptake this technology. Next slide, please. That was it. So that's that was the overview of the beta phase. And yeah, we're ready to take any questions.
Great, thanks for that presentation. There's just one question in the chat, but I think it was sort of addressed in the last portion of your presentation, just around ESO involvement, particularly for a future phase, and what their involvement might look like. Did you want to expand on that more, or?
Yeah. We're happy to. Yeah, thanks, Ellie. So yeah, good question. They are involved in the project. They're in a project advisory role. We did invite them to partner, but because they run the market as it currently exists, they yeah, feel it's sensitive, I guess, as to be partnering in some of these projects. But yeah, they're very supportive of the project and they're keen to learn. So we have the National Grid ESO from GB, obviously, involved, but we also have TenneT from the Netherlands and RTE from France. And the idea is that we're really keen in this project, to be an internationally leading project, but also it's really important for the sake of the OEMs and the developers who are going to be developing these solutions, that they are meeting the same requirements across borders, because otherwise, if there's different requirements in different countries, then the cost for every individual country is going to rapidly increase. So we're keen here to disseminate not only to the GB market and the GB market setter, the ESO, but also to a number of other leading TSOs. And the idea is, once we get the main TSOs involved with offshore wind to recognise and to understand what offshore wind can provide, then further international dissemination and rollout should be pretty smooth. But thanks for the question.
Great. Thanks for that. I don't believe that there are any more in there. But this Q&A function will still be available, and the team will be on to answer any other questions for SIF Blade. So thank you to SIF Blade for their presentation. We are now going to a 15-minute break, and we'll see you back shortly. Thank you. Is back online. We'll just give it a few more moments. Right, so I'd just like to welcome our next project, which is Connectrolyser.
Thanks, Ellen. Yeah, so hi everyone, I'm Ben Turner. I'm an innovation engineer with UK Power Networks, and I'm presenting Connectrolyser with Hydrogenous. Mary, if you want to say hi.
Hi everyone. Yeah, I'm Mary Trinan from Hydrogenous, and have been working with UKPN and our other project partners on the Connectrolyser project. So looking forward to sharing that with all of you today.
Next slide, please. So the UK government have committed to 10 gigawatts of low carbon hydrogen by 2030. And 6 gigawatts of that needs to come from electrolysis. Now, previously, hydrogen was produced by cracking natural gas, but as we have to move away from fossil fuel use, electrolysis is probably one of the best options for this. Now, just to sort of give you a rough idea of how this works, to give it its proper, technical term, you're zapping water with a lot of electricity, which essentially splits up the molecules. And you have an outlet of hydrogen gas and oxygen. So that, looks on paper like quite a green solution to producing low carbon hydrogen. And yeah, we've got a kind of diagram of it there. And I think that really explains the relevance of a distribution DNO like us being involved in this project because of the massive electricity requirement that you will need to operate an electrolyzer. Next slide, please.
So thanks, Ben. So we as Hydrogenous are a low carbon hydrogen developer. So we are largely focused on delivering those targets that the government has set for us and saying, how can we find opportunities to create decarbonization pathways for entities that might want to use low carbon hydrogen to decarbonize their operations. So when we're going out there and trying to find these opportunities, there are lots of things that we are considering. So this diagram is showing several of the different variables that we have to think about. If we start on the right, first of all, we're thinking about who might our customers be. So who are the different entities that might be looking to use hydrogen to decarbonize? So that could be several different types of organizations. That could be a transport use. So the kind of thing that comes to people's mind is hydrogen buses, for example, or that could be industrial users. So a factory that might be looking to make the transition from using natural gas to hydrogen. So we're looking at different opportunities for who might those different end customers be and what might their hydrogen requirements be. So they might have different operational needs, different timelines, different volumes of hydrogen that they might be looking for, different pressures of hydrogen. So there's several different variables that you have to consider when you're thinking about, okay, you start with who and what they might need. Then we move to the middle and think about, okay, we use that piece of kit that Ben was just describing, an electrolyzer. That's the kind of the core of our hydrogen production facility, which is the piece of technology that we need to create the hydrogen to convert water, zap it with electricity, as Ben said. I love that analogy. That's how my brain works, is okay, you're just zapping the water with electricity to create the hydrogen. There are several different types of electrolyzers that you might want to use. That have different limitations, that have different outputs, that are available or less available, and several different things that we'd have to consider what type of electrolyzer technology might we want to procure to best meet our end user needs and also be the most cost efficient. We also need to consider, do we need to compress the gas? So depending on who your end user is, you might need your hydrogen at a different pressure. So you need to compress it to be appropriate for who your end user might be. When it comes to the compression, what type of compressor might you need? What size would it need to be? When you might need to operate it? You also need to think about, do you want to have any kind of redundancy built into your system? So do you want to have some hydrogen storage on your site? What size might you need? How much? How you might want to operate it? Again, all going to be determined by your end user. So for example, if you have a transport user, you might have different operational needs, and you might want to have a different amount of backup based on their kind of operational profiles as opposed to a factory. So we have to consider, when we're thinking about our hydrogen production facility, we're thinking about all these different variables and trying to right size it appropriately. And that's, of course, when we come to run all of that, we need electricity, and we need relatively high volumes of electricity. And that's when we come to the distribution network and we say, okay, how much power are we going to need to run all of those processes and to run them efficiently? So that's when our relationship and our interaction with the DNO comes in. We need an electricity connection. So you would go through the normal process for connecting any type of asset to the distribution network and go to UKPN in this case, who we've been working with, and say, okay, we want to connect, and this is how much we want to connect. So that's where the relationship comes in between the hydrogen developer and the electricity DNO. Go to the next slide, please.
Mm-hmm. Yeah, so connecting with a DNO. So traditionally, people would come to us and say, I have an electricity requirement. This is how much I need. And we would come back to them with a quote, how much that's likely to cost and how long it's going to take us. if you look at the current landscape, there are so many industries that are electrifying. It only takes to consider the car industry, and you realize how much more electricity is being asked of by DNOs. So because of this, the wait time to get connected is getting longer and longer as we're trying to cater to so many different industries that we hadn't otherwise worked with. So that's going to be a problem for this growing market of green hydrogen, of all of these electrolyzers that are trying to connect to our network and start producing hydrogen in a green way, in something that is technically, you know, helping us achieve net zero. So to do this, what we offer is different types of connections, like a flexible connection, curtailable connections, and various other things. Now that means that we can't guarantee that you're going to be receiving power 100% of the time. So yeah, we might send a signal to your system and say, tomorrow we're going to need to turn you off. Or yeah, we can send you electricity overnight when maybe the people aren't using it as much. And yeah, it's about negotiating that with the person that's asked for the connection. And then this also stops us having to reinforce the network more and more, because we're not sort of needing electricity at peak times because of your connection type. And this is something that is new to hydrogen and hydrogen production facilities. So it's something that this project has been exploring. And next slide, please.
I'll just add one thing before we hop to the next slide there, sorry. This is essentially the crux of our project. So we knew that these types of flexible connection offerings existed, and they have existed in several forms, you know, across the years as the DNOs have been innovating around this challenge of connecting sooner and finding ways to connect renewables to the grid and allow them to operate flexibly. But as Ben said, this hadn't really been considered for how might you treat a hydrogen production facility or a hydrogen hub as a flexibility resource. So we said, well, let's explore how you might have an opportunity rather than a challenge to use this concept of flexible connections and flexibility and apply them to hydrogen production facilities. Because of the technology types that I was talking about around electrolyzers, they have the capability to be extremely flexible. They can respond in near to real time and ramp up and ramp down, you know, immediately. So there was a big question mark that we said, okay, well, is there a huge opportunity here that can really help the industry, the hydrogen industry, to meet those targets that the government has set and enable us to more quickly connect more low carbon hydrogen facilities and meet those net zero targets. Next slide. Thank you. So this is where our whole project has been focusing. So the Connectrolyser, as we've called it, is an optimization logic and tool that is that piece of the puzzle that allows you to connect and operate hydrogen production facilities flexibly. So what we've been developing as a part of this last 6 months is a tool. The requirements for a tool and a testing version of that tool that allows us to optimize the entire hydrogen production facility. So optimize our hydrogen production, all of those different factors that I was talking about, your compression, your storage, some predictive capabilities around weather, when you need to meet your end user needs. But the primary rule for that optimization is the electricity requirement from the DNO. So under a flexible connection, if you agree to connect via flexible connection with UKPN, you say that I accept that I might be curtailed, so I might be turned down, I might not have access to all of my electricity capacity all the time, but I can connect sooner and for a lower cost because there isn't that reinforcement requirement from the distribution network. So the primary optimization rule that goes into our piece of technology is you have to be able to respond, the hydrogen production facility has to be able to respond to a curtailment instruction from the DNO and optimize your hydrogen production facility in real time in response to that signal. So the primary rule in terms of the optimization is the DNO is sending you a signal that says, okay, you're either turned all the way down or turned some of the way down because we have a fault on our network, and you have to accept that condition because we've accepted that condition as a part of our connection agreement and optimize our system accordingly. So we have been working to develop all of the logic that sits around that, the modeling that sits behind that, and all of these different factors that need to be optimized in response to that curtailment instruction. So this Connectrolyser, our optimization tool, integrates directly with the DER management system that sits within UKPN, or the equivalent with another DNO, and sits exactly in between the DNO and the rest of the hydrogen production facility to optimize based on that curtailment instruction. So this is where the focus of our innovation has been. Next slide. Thank you. So to do that, there have been several different things that we needed to kind of explore in terms of potential limitations and enablers as we have gone on. So we started out saying that we know that there are existing flexible connection products that exist within the DNO. Let's make sure that the limitations of a hydrogen production facility fit within the requirements of those connection products, or might they need to justify a new type of connection based on some of the factors that I talked about earlier. So we evaluated the different connection products and evaluated what's called the D code, which is the distribution code that all DNO licensees are subject to make sure that there would not be any changes that would be required to that code in order to connect and operate these hydrogen production facilities flexibly. So luckily, they were in compliant with existing standards. We did identify some opportunities for improving processes or learning about how different connection arrangements might evolve over time, or how different flexibility products might evolve over time. When you consider how hydrogen production facility might be a flexibility asset. We also looked at some of the technical and commercial constraints that barriers and enablers that could allow these hydrogen production facilities to operate flexibly. So as I said earlier, several electrolyzer types can respond in real time. So there's an opportunity for extreme flexibility there, and they can quite safely meet the ramping requirements that are set out within a flexible connection arrangement, which is that it needs to be a real-time response. If you can imagine there's a fault on the network, you need to be able to respond in real time to protect the network. We then looked at what the system requirements would be for our hydrogen production facility. So as I said, we looked at some personas for what the different hydrogen end users could be. So is it a transport end user? Is it an industrial end user? Is it a mix? What does that do to your hydrogen production facility, to what your electrolyzer might be, what your compression might look like, what your storage might look like, and of course, and most importantly, how much electricity you might need, because that informs what your connection request would look like to the DNO, and what your flexibility, your flexible connection arrangement might look like in terms of your curtailment volumes and your costs. And then ultimately, as all of that was going on, we were designing the Connectrolyser itself. So the optimization logic, the tool, the functional and technical requirements for delivering it, and the software, essentially the technical specification for what would ultimately be a cloud-based optimization software. And then we talked about what a demonstrator would look like for this type of innovation in real life. And I'll leave Ben to talk about that a little bit when we're starting to talk about what a beta phase would look like for this project. But we wanted to think about what the things that we would want to test from a DNO perspective, the different types of network conditions that we would want to test, and how that would influence your hydrogen production. Next slide. Over to you, Ben.
Yes, so the early sort of cost-benefit analysis that we've carried out as part of this project, as I mentioned before, the aim of this is to reduce the need for reinforcement of the network. And also that will help hydrogen hubs connect earlier because they're not part of that queue that we also explained. So our initial model has estimated that a hydrogen hub could connect to the grid 3 years earlier. So that's 3 years of producing hydrogen when maybe they otherwise couldn't have, making money 3 years earlier. So yeah, we believe that's a strong benefit for hydrogen hub developers. In terms of network reinforcement, across all of the United Kingdom, we estimate about 3.4 billion would not have to be spent on allowing all of these hydrogen hubs to connect. So also another key benefit for the network and customers of all DNOs. And with this, avoided curtailment becomes the carbon reduction. So we're not spending money installing lines, digging up ground to lay cables. We're also displacing fossil fuel use because of the potential benefits that hydrogen can have as we start to use it more. Yeah, and that leads me on to the sort of final slide, which is that's our plan on our page for the future. But if we just sort of skip past that one, I'll go to the summary. Actually, yeah, sorry, go back. Yeah, so sorry, the plans for the future. We plan to develop the optimizer, the Connectrolyser, as it were, the smart control system. We then plan to build a digital hydrogen ecosystem, which is essentially simulating how a hydrogen hub would operate. We would then test the smart controls, the optimizer within this ecosystem to allow us to iterate it and make sure that it works how we want it to. And then whilst we're doing this, what we would do is test different types of flexibility services. So what type of connection works with a hydrogen environment and how will it respond to that kind of thing. And we'll use this to develop a sort of playbook that will allow other hydrogen hub developers to see the work that we've done and maybe, allow them to connect to the grid a lot easier, and also be a sort of information piece for other DNOs. So if hydrogen hubs come to them, they can sort of refer to this for how they can connect to the grid and really facilitate this sort of influx of green hydrogen. So next slide, please. Yeah, just that's our sort of final slide, really. Just we really do believe that there's a lot of benefit for this. It can make DNO's job easier. It can really allow hydrogen hub developers to connect to the grid faster. And we also believe that it might help them actually run their plants more efficiently. We believe that the DSOs can develop their really innovative flexibility offerings. And overall, society can benefit by a really exciting industry that is in kind of early days, but is showing really significant growth. Thank you.
Great. Thanks for that. That was a really thorough presentation. We do have got a couple of questions here. So one of the questions I had to ask was what sort of alignment is this project looking at in terms of what the hydrogen economy work that DESNEs are doing, and how are you fitting what they're doing in line with in line with this project around sort of like flexible versus stable connections? Are they sort of at odds with one another, or?
I can answer that one. Sorry, I've got a bit of sun in my face there. I would say that they're absolutely in line with each other. In parallel to this project happening, there's what's called the hydrogen allocation round, which is an incentive mechanism for low carbon hydrogen sites to be developed. And we are closely involved with that. And this challenge/opportunity around having the volumes of electricity required to operate hydrogen production facilities will be something that any hydrogen developer is facing, and the costs are high. So this is extremely beneficial to the industry and is in line with innovation in the hydrogen space, because there's an opportunity there for there to be cost saving when we're going into these incentive rounds that are kind of happening in parallel to this innovation work. So I would say that they're largely aligned, and any learnings that learnings that have come from this are interesting to kind of the hydrogen industry more generally, because they're always going to need to have an interaction with the DNO. So there's learnings from not only interacting, but also from the potential commercial benefits of connecting sooner and at lower cost.
Very thorough answer, thank you. Just one kind of additional point to the question. So are there other networks that you plan to engage with or test your assumptions on based on like non-firm connections?
I think that's a critical part of what we want to capture within the kind of the playbook for how this would work, because we understand that all the different DNOs have different approaches to flexibility, and that includes flexible connections and flexibility offerings. So the idea is that this should be able to work for, you know, any type of flexibility connection, and that's where the concept of the playbook that Ben was talking about is what we'd want to develop, to make sure that there are some fundamental building blocks that would be the same across any DNOs. You know, what's the type of data that you might need, what operational profiles look like, what kind of information needs to go back and forth, these kinds of things that we can be able to interface with other DNOs and inform kind of the holistic view rather than just a singular a view of how that might work. But Ben, do you have anything else to add to that?
Yeah, just that part of the work we plan to do is look at how would you integrate with our management system on our network, and there's different management systems across the United Kingdom. So if we're going to develop a smart optimization system that can only work in one area of the UK, we're not exactly helping a GB-wide benefits. So there's definitely work to do there. And yeah, we do plan to engage with other DNOs across the country.
Great. I think that's all of the questions I had. There are no questions in the Q&A, but please do pop those in there. So the team who is on at the moment can answer them. It sounds like they're very equipped to answer your questions. So yeah, do use that facility. And with that, we'll move on to the next presentation, which is artificial forecasting.
Thanks, Ellen.
Thanks, guys.
Thanks.
Good afternoon. Can I just check that you can hear me okay?
We've got a little bit of background noise.
I'll talk for a moment. Sometimes that helps to equalize it. I'm in a reasonably quiet space. Is it me or someone else, perhaps? Is that good enough?
Yeah, that's fine. Thanks.
Okay. Yeah, do you want to move to the next slide then, please? And the next one after that. Great, thank you. So Northern POWERGRID are the DNO for the North East, Yorkshire and North Lincolnshire. We serve 8 million customers, and that's through 600 high voltage substations and 60,000 low voltage distribution substations. My name's Neil Wade. I'm a forecasting team leader in our Energy Systems Directorate. So this project's about forecasting. DNOs have always needed to forecast in order to maintain and develop the networks safely and economically. But forecasting needs are increasing both in complexity and granularity due to the changing requirements of the energy system. So we've got new loads coming on, new ways of operating the system. One aspect of this complexity is the use of flexibility to avoid network reinforcement. This means that we need more information than just the maximum demand seen on the network over the course of a year. If that was the only information we had, we would procure flexibility for every hour of every day, just in case we need it, which is in effect what we do if we use an asset-based solution to create capacity on the network. Because it might be possible to address the investment inefficiency of building new assets just for peak times, we might be able to address that through customer flexibility. So at Northern POWERGRID, we have a flexibility first regime. And what this means is that when we identify a capacity shortfall, we look for flexibility options before turning to that asset-based solution. So at the core of this project, we've developed a short-term forecasting capability so that we can quickly and cost-effectively implement refined flexibility service requests across every part of a network that has got suitable data collection in place. So I mentioned we've got 600 high voltage substations. They already have that measurements in place. And by the end of this price control period, so by 2028, we'll have about 12,000 of our low voltage substations with suitable monitoring. So by increasing the information about our capacity constraints in the short term and sharing this information with flexibility service providers, in addition to only calling the flexibility when we need it, flexibility service providers will also be able to add new customers to their portfolios to meet the more precise flexibility requests that we're making. So within this project, Northern PowerGrid have provided network data and the use cases for the project and looked at how we would deploy it within our systems and across DNOs across the UK. But this has been delivered alongside the experienced flexibility service providers EV Energy and Oak Tree Power in order to bring in their views of these enhancements that we're making to provide better information on our flexibility service requests. The short-term forecasting models have been developed and assessed by experts in artificial intelligence faculty, and they're now going to come in and take us through the project, he says with confidence.
Thanks, Neil. So let's move on to the next slide. Thanks, then, Andrew. Please. Excellent. Yes. So my name is Andrew Glennie. I've been overseeing faculty's contributions to the artificial forecasting project. And as Neil mentioned, we come in as technical AI experts working with MPG, Oak Tree and EV Energy. So what we've done at Alpha over the last 6 months or so is develop operational forecasts across MPG's network of primary and secondary substations. So looking at a horizon, say the day, week and month ahead. And that really fits in with the flexibility first agenda that Neil was referring to. So the ambition here is to make better flexibility procurement decisions. So, and that's by using the forecast to identify windows for flexibility procurement months in advance, but critically enable the refinement of dispatch requirements from flexibility service providers closer to the time of need. So improving the deliverability of these services and potentially enabling a wider set of asset owners and operators to take part with this greater certainty. So Alpha has delivered functioning proof of concept forecasting models at all of these levels. And I will now hand over to the team to take you through the specifics of what we did and what the plan going forward looks like. So I'll hand over to Rukaya from our team. And if we can move to the next slide, please.
Thank you, Andrew. So hi, everyone. My name is Rukaya, and as mentioned, I'm from faculty, and I worked on the commercial and the project management aspects of this project. So in terms of the overview and the work carried out at Alpha, this was split across four work packages. And for the purpose of this presentation, we'll just focus on the first three. So the first work package focused on user research with an aim to understand MPG's objectives around using flexibility and how a solution could influence their decision-making processes. The second work package focused on delivering a proof of concept forecasting solution. So here we tested different AI and machine learning approaches across the different scope items. And we also involved the flexibility partners to understand the broader application and benefits of the solution beyond DNOs. And the third work package focused on the business case of the solution. So using the insights that we gained from user research, the data collected, and also the flex partner involvement as well, to understand the potential benefits that can be gained from the project. Next slide, please. So in terms of the results achieved on the user needs workstream, so we held a number of user research sessions with MPG's forecasting and flexibility teams to confirm the business application for the solution. And so that is essentially that MPG will be using the short-term load forecasts to specify their flexibility dispatch requirements at much shorter timescales compared to what their current process is. And this will enable them to procure and interact with the flexibility market in a much more economic and efficient manner. I won't go into too much detail on the results of the POC development and the benefits work stream, as these will be discussed shortly. But in terms of the results obtained across the work stream at Alpha, we feel we've demonstrated a clear case for the project to continue. And so now we're looking ahead to Beta, where the ambition is to develop a solution that in the first instance can be deployed within Northern PowerGrid's environment, but also a solution that we think is applicable for other DNOs as well to utilize. And with that, I'll hand over to Katrina to go over the technical approach and present the findings for our proof of concept.
Great, thank you. So yes, if we can go on to the next slide, please. My name is Katrina. I'm a senior data scientist at faculty, so I've been leading on the technical development of the solution. But before we go into what that looks like, let's just stop and look at exactly what we're trying to forecast. So as previously mentioned, we're forecasting at 2 levels, EHV to HV level and HV to LV level. At the EHV to HV level, we have half-hourly data on 3 signals: gross active demand, customer export, and net active demand. So gross active demand is the total demand for electricity at a substation. The customer export then is the generation that's going into that substation, some of which will be used to offset that gross active demand. And this leads to a net active demand signal. This is actually what the substation sees, but it is essentially the demand with the generation netting off some of that demand to produce a net signal. And we can see how that works in that chart in the bottom left there. One thing to note on this, although it is net active that MPG really care about forecasting, a decision was made early in discovery to do that as a combination of separate forecasts for gross active and customer export. The reason for that being that customer export is probably the hardest of these signals to predict, and we're going to see that in a couple of slides' time. But with the move to net zero and the rise of embedded generation, that is the one that is going to become an increasing part of the signal. So if we don't get that right, we're going to get the modelling more and more wrong over time. At HV to LV level, the situation's a little bit more straightforward. We only had net active data, so that's what we're forecasting. So if we move on to the next slide, we can talk about the technical approach. As I said, we're forecasting at EHV to HV, gross active and customer export separately. So in terms of gross active, if we look at that data, it is actually very nice time series data. It is nicely autocorrelated. There are nice periodic daily and weekly patterns, and therefore this is very amenable to traditional time series forecasting approaches such as Saramax and Profit. We also looked at this, modelling this using a Bayesian linear regression. That's not technically a time series approach, but if you use the right input data and you kind of create the right time series features, you can use it for forecasting in this space. And actually, we've seen it work very, very successfully in other projects. Indeed, it was also our forerunner in this particular project and is our recommendation going forward for Beta. A couple of other conclusions from this particular work stream, because the data is being collected by sort of real world systems or a real world network, there are a host of data quality issues that we had to consider, and we built out an ETL pipeline that was automated and scalable across MPG network to handle this. So having built out decent data quality and decent forecasting capability, the focus at this particular work stream at Beta very much needs to be on communicating uncertainty and error in the model such that it can most usefully be used for that refinement of flexibility provision that was discussed earlier. If we go on to the next slide, we can see a slight difference with the customer export signal. As I've said, this is very much the hardest of the signals to forecast. There is no sort of particular periodic pattern. And indeed, if we look across substations, we see very, very different behavior across different substations. This led at Discovery to us developing an approach whereby we were going to consider groups of substations based on the majority fuel type feeding into that substation. So is the embedded generation feeding into that substation mostly solar, for example, or mostly wind? And if we take that group, how do we then understand that group as a whole? And what extra data can we use to better forecast that group, in addition to the sort of data that people historically use, calendar features and weather data? So for example, does including national demand forecast help? Does including operational marginal data help? What we found from this particular work stream was that actually, although grouping those substations was a good approach, grouping at the fuel type level, when you consider all of MPG substations, isn't quite the right level to do things at. If you look at the behavioral patterns in the data, you do see groups of behavioral patterns, such as data that is very spiked or data that has a sort of on-off pattern, but those cut across fuel types. So moving forward at beta, we would look to actually group the data based on its historical pattern, not based on fuel type. And this also bypasses any data quality issues with assigning fuel types based on the embedded capacity register. It also allows a clearer understanding of what this extra data can do for forecasting, which was very mixed at alpha because of that slight heterogeneity of behaviors in different fuel types. Obviously, those two signals can be then added up to produce our net forecast signal EHV to HV. If we now move on to the next slide, we can talk about HV to LV forecasting, where the data is somewhat periodic. There is definitely a periodic pattern there, but it's a more flexible system and is going to need a more flexible modeling approach. So a couple of the approaches proposed here, Profit, which is a sort of time series, well-known time series package from Facebook's owner Meta, and also a sort of neural network approach that is specifically designed for sequential data. We also wanted to take account in a third approach of the fact that these substations have sort of natural groupings in terms of their customers. So, for example, some stations will have all domestic customers or all like commercial customers, for example. So can we actually group those and use information shared among that group to improve the forecasting? What we found in this particular piece of work is that actually overall, the temporal convolutional neural network approach was the most performant, and that's the recommendation for beta. But actually, the work to look at hierarchical modeling did successfully produce about 8 different profiles for different substations. And that not only can be used for refining models at beta, but also potentially for things like supporting further understanding of flexibility procurement at this particular level. So those are the technical approaches. I think I'm now handing back to Rakaya, who's going to talk a little bit about the benefits.
So myself this time. So
let's flick over. Sorry.
No worries. Let's flick over. Yeah, this kind of introduces the last segment really around kind of looking forward and beta planning and how we see the projects in the longer term. So yeah, what we're really doing now is preparing for beta and all the evidence and business case required for that. And part of that is, of course, trying to assess the potential benefits the project could generate. And there's 3 main channels for that we've identified. One is the kind of classical benefit related to flexibility around, the potential deferring of reinforcement expenditure through the use of market-based solutions, and kind of going over and above what's set out in the ED2 plan and looking into ED3. Secondly, around environmental benefits generated by this solution, that's partly by curtailing demand, but also using or providing opportunities for FSPs like Oaktree that optimize sites based on environmental impact, for example. So, expressing savings as a ton CO2 equivalent. And lastly, around new revenue streams, in particular for FSPs. So partly that's through improving the deliverability of existing or flexibility service requirements, and also by shortening the window for the service requirement, you can improve unit prices and also enable FSPs to take part in other markets as well. So a whole range of benefits we're looking at here, and we're revising that within the beta application. We're currently estimating an NPV of around £30 million across ED2 and into ED3. But that will be refined going forward, and I guess Katrina will take us through next the kind of lessons learned and what beta looks like, and then we'll wrap up. Thank you. Next slide,
so yes, if we move on to the next slide. So yes, in terms of sort of the key takeaways of the project as a whole, what did we learn and what are we doing going forwards? So firstly, I think one of the key learnings was that data quality can be assessed and corrected automatically at scale. We've demonstrated that with robust pipelines at EHV to HV, working on over 400 substations. And in terms of the modelling approaches specifically then, efforts to improve accuracy should focus on where there is most gain to be had. At the gross active level, we already have pretty good accuracy, whereas customer export, for example, there's a slight refinement that needs to happen to that particular approach. One of the things I think we've definitely discovered is that context for the data is key. So actually understanding substations at the level of functional groups, whether that's in the customer export data or the HV to LV data, is going to allow more accurate and robust predictions, but also allows a certain level of decision support on the ground when MPG are working operationally dealing with generators and flexibility procurement. User testing has demonstrated a need to be very clear about the integration between forecasting results and flexibility provision. There's no point in having a good forecasting tool if you're not using it. And then having developed a strong POC models, there should now be an increased focus on the communication of those results. And as I've mentioned previously, the sort of uncertainty and error that allows MPG and partners to make decisions on the ground. So what does that all mean for beta? I think if we go on to the next slide. Essentially, then we're sort of focusing on 4 different things. There will need to be at beta a sort of further user research and user testing refinement period that actually, given that we want to make as much of this data available and as much of the metadata available to DNO customers as possible, how do we make that very easy for example, flex partners to ingest? What does that need to look like in terms of a solution design? I've touched on previously what model refinement needs to look like, for example, looking at different behavioral groups at the customer export level. And this needs to be a deployed solution. That means we need to actually set up the infrastructure for making sure that this can actually work day in and day out for MPG. And then finally, underpinning that, there needs to be work on the solution commercialization. So actually, how does this then maximally benefit both MPG, but also the flexibility service providers in order to improve flexibility procurement, stimulate that market, allow things to sort of flourish in that space. And that's that for that slide. I believe that was the last slide. Yes, so I guess any questions?
Just a reminder to everyone who's still on that there are there's the Q&A function that's available. I'll just open this up. This one is more in relation to other show and tell presentations. But I did have a question that was more in relation to the project. So is there any plans to have you taken any learnings from any other similar projects that say other DNOs or sort of DNO providers in other places have done, or is this quite unique to Northern POWERGRID?
So I'll answer that first, and then maybe other points from my colleagues. So yes, we've very much tried to look at the landscape in this area because it's clearly something that all DNOs are moving towards, providing shorter term forecasting to be able to refine flexibility markets. So I guess of note, the SSEN transition project had a forecasting element in it, so we looked at that, and I think one thing we've found is that there are refinements to forecasting or refinements to requests for flexibility being provided by DNOs, but sometimes it's not absolutely clear what's going into that forecasting solution, how it's being generated, and what information is provided to the flexibility service providers. So in our discussions with the FSPs, they're very keen to get information about the flexibility requests, sort of above and beyond just we want you to provide this many kilowatts over this period of time, but to understand about the likelihood of that, when the adjustments can be made and things like that. So it's about, I think our observations are that there is information out there, but it's and we want to enhance that and make it more usable to the FSP so they can develop their products in the market.
Great, thanks for that. We have another question here, which is from an anonymous attendee. What was the time series data you were working with? Real power as a function of time?
Yeah, so it's half-hourly data. So essentially for the high EHV to HV data, we provided 5 years of half-hourly site level data, so the kilowatts at our primary sites. For secondary sites, we used a subset of our monitors, about 800 monitors, again, half-hourly data, and that was over a period of 3 years because we started our rollout of LV monitoring about 4 years ago. So yeah, we've got sort of good quality data going back about 3 years. But yeah, fundamentally half-hour active power that we, and as Katrina mentioned, it's both we've got the data from the substation loading, but also what the customer export is, so what the embedded generation is producing on a half-hourly basis across the network.
Great, thank you for that. Just one more question here from an anonymous attendee. So in terms of the plan for beta, I think the question's asking, what is the plan for integrated network testing in beta, and what advantages would this type of demonstration give?
Yeah, I'll just add one more thing to the last question I thought of. We are publishing all of the data as well. We're just going through our, we have governance around publishing all data, but on our open data portal at Northern PowerGrid, the data will be available in the coming days. It's just, like I say, going through our governance to make sure we're publishing appropriate data sets. Yes, integrated network testing, that's a big part of this, because what we recognize is important in the beta phase is that we have a system that can be deployed within our IT architecture, which is not simple due to security and sort of the combination of systems that we have in order to run the network. So for instance, our EHV-HV data is collected in a different system to our HV-LV data. So there needs to be some different approaches to how we extract and process that data. So yeah, the integration within, I'm presuming the question is within the IT system, but yeah, drawing live network data, processing it near real time, and producing a forecast near real time. But yeah, there's an awful lot of subtleties and issues around that we're working through in the beta phase.
Wonderful. Thank you. Thank you for that presentation. Those were really thorough answers as well, which we always appreciate. So we'll now go across to our final presentation for today, which is HyNTS HyNTS waste heat recovery for electrolysis.
Yeah, thanks, Helen. Good afternoon, everyone. So my name is Matt Hammond. I work in the innovation team at National Gas. I've been leading on our project, which is looking at waste heat recovery on our network. So if we can skip on to the first slide, please. Perfect, thank you. So National Gas own and operate the National Transmission System, or NTS, in the UK. So that's the UK's high pressure gas network, which takes natural gas from the terminals on the coast, so up at St Fergus for North Sea gas, for example, and Bacton, which connects to Europe. And it transport it basically up and down the country, depending on where the demand is. We connect to power generators, so gas-fired power stations, as well as large industrial users of natural gas. And additionally, our gas is also passed on to the gas distribution networks, who distribute the gas onto homes and businesses as well. This project is very much focused on our compressor stations and our compressor units. So our compressor units are what we use to drive the gas around the network to where it needs to be. For example, all the gas that's coming in up in Scotland isn't going to get used there, so it needs to be essentially pushed south into the rest of the UK. So our compressor units are primarily driven by gas turbines. So the bottom right diagram shows approximately how it works. So we combust natural gas. We actually take the natural gas from the network itself and use that as a fuel. The hot exhaust gases drive a power turbine, so converting that fuel into mechanical energy, which spins the gas compressor, which is actually what is giving rise to an uplift in pressure and flow rates in the network itself. So if we can flick on to the next slide, please. Thank you. So we have 22 compressor stations on the NTS. Each station has multiple compressor units. Mostly this is for kind of redundancy and resilience. So if a unit goes down, we are still able to operate our compressor system. So as I mentioned, these units primarily are gas turbine driven. So we've got 74 odd units. I think it's about 65 of them operate small gas turbines to provide that power. The others are electric motors. So the gas turbines burn natural gas. This obviously produces carbon dioxide and also produces waste heat, which is where our project is mostly focused on. In terms of the opportunity then, heat recovery is used across a range of industries today. Primarily, you can use the heat for multiple things. So you can use it as steam for steam networks, provide heat to other processes. You can generate electricity, and also we have been investigating whether we can use that electricity to actually produce hydrogen as well, and actually feed that as fuel into the gas turbines themselves to actually address the CO2 problem as well. If we can flick on to the next slide, please. So this gives a very sort of high-level overview of what the project, how the project's been set up. So some of the key objectives at the top there. So discovery was very much about working out if it's a feasible thing for us to do. Is it something that's worth doing? We were very much focused on feeding the steam into an electrolyser to produce hydrogen. But as it's kind of developed through alpha, I think we found additional use cases for the waste heat recovery, and it's looking like it can be quite a flexible thing for us to be able to do. There's different things we can do with that recovered energy. The alpha phase is more about the system design, what the technical capabilities and how it will essentially interact with our existing assets and the operation of our sites and our network. Also looking at the safety case for deploying it on site as well. And beta is going to be about actually demonstrating this technology and developing the evidence that we need to say, yes, this works and this is a good idea. So key partners on the right there. So Alfa Laval are the designer and supplier of the waste heat recovery system. Cardiff University have been providing some kind of peer review activities, and also in the alpha phase, they've done some system optimization through some modeling, which they're going to talk about in the slides, which has been very useful for us to understand what the system could look like when we deploy it. Modeling is very useful in that sense. Anglian Water, we're looking at the design of the water supply system. So obviously the heat recovery system needs a water supply, but obviously when you bring electrolysis into the equation, that needs very pure water. So the design work was very much focused on the sort of worst case, if you like, is if you have that hydrogen production element. Hydrogenous are a developer of low carbon hydrogen hubs in the UK. They also support the Connectrolyser project, and they've also been supporting our hybrid storage project as well. So they've been providing some very useful insights in terms of electrolyser operation and just general commercial opportunities when it comes to that hydrogen production element. And SGN are a gas distribution network, so they've been supporting and feeding in sort of use cases from the distribution side in terms of heat recovery. Can we flick on to the next slide? And that should be handing over to Alfa Laval to cover some of their work in alpha.
Hello, yeah. Good afternoon. My name is Richard Price from Alfa Laval. If someone can click the button, please, it should advance. Thank you. So for the alpha phase of this project, the first thing was to agree on an operation philosophy. The study site was the Cambridge compressor station. The Cambridge compressor station has 3 gas turbines, two older units, which are the Avon A20s, and a newer Siemens unit. So we have 3 gas turbines and 2 types. It was agreed to generate high pressure steam. The high pressure steam can then be used twofold. The first is to generate some low pressure steam for supply to the electrolyzer. So this reduces the power requirement of the electrolyzer for producing hydrogen. And the second and bigger part was to drive a steam turbine generator to supply electric power. So this electrical power, new source of electric power, can be used for the electrolyzer, which is quite a heavy demand on electric power for producing hydrogen, for all the other new equipment that would go on site associated with this system. Also the existing site requirements, which is around 600 kilowatts at a peak, and possible export to grid. With the waste heat, we may generate some surplus power, which can be exported to the grid for reuse. So we had 3 fuel cases. The first one, base case, being 100% natural gas, which is what the gas turbines operate on now. Second case was a blend of 25% hydrogen with 75% natural gas, and final case was 100% hydrogen. Now these slightly vary the exhaust gas composition that comes to the waste heat recovery system from the gas turbine exhaust. We also looked at 3 load cases: a maximum case, which is the maximum load case of the 3 gas turbines, a middle case, and also the minimum gas turbine load, which is the minimum load at which they compress gas. The schematic there shows the main sort of steam, water, and exhaust gas system as we developed it through the project. Next slide, please. One more point. Sorry. The existing gas turbine exhaust data was collected from existing operational and original design data, and we also visited site on 2 occasions to look at the system installed and to gain knowledge of the layout that we would come up with. Okay, thank you. Next slide. So this shows an aerial view of Cambridge, and you can clearly see the 3 sort of compressor houses. The central one and the one to the left are the older units A and B, which are the Siemens Avon A20 gas turbines installed early in the 1970s. And the unit on the right is the newer unit, Unit C, which is a Siemens SGT 400, installed, I think, around 2003, something like that. So you can see the layout there of the 3 gas turbine-driven compressors. Next slide, please. So the waste heat recovery boiler was designed based on the exhaust gas rate. We had up to 248 tons an hour of exhaust gas from the gas turbines. And this exhaust gas for the Avons is over 400 degrees, and for the Siemens unit is over 500 degrees. And by extracting the heat from those exhaust gases, we reduce the exhaust gas temperatures to around 134, 164 degrees centigrade, which will change the emissions from this. Now, this exhaust gas energy results in up to 20.6 megawatts of thermal energy that is recovered from these exhaust gases. And from that, we can generate 25 tons an hour of high pressure steam, which will be superheated to just under 350 centigrade. Next, thank you. So with this steam supply, we can then size a steam turbo generator. That steam turbine generator will generate electricity, and at a maximum case, it's 4.8 megawatts. And for the Siemens unit, the newer gas turbine, it drops a little bit to 4 megawatts. And at the minimum load, it's around 0.8 megawatts. So this is electrical power that we would generate. So you can see there the power generation on the graph, the power generation of the steam turbo generator, depending on the heat input and the compressor load of each of the gas turbine types. So first project documents were produced, and we got a lot of proposals in for the main equipment so that we could design a system. Next, please. And a new layout was drawn, which I'll take you to now. So here, sorry, yeah. So here is the layout drawing, if you can remember the previous aerial photograph of the 3 units. So what's been added is the waste heat recovery boiler. Now we have to connect to the 3 gas turbines. So we have quite a lot of ductwork to take the exhaust gas from the existing exhaust stacks to the waste heat recovery boiler. The waste heat recovery boiler needs a feed water tank. And that boiler will then feed a steam turbo generator, which will go in a new building between units B and C there. And then the final steam under vacuum conditions is condensed back to water for feeding back to the waste heat recovery boiler through an air-cooled condenser, which are the 6 updrafted cooling fans there. Next one, please. Sorry, can you go up one and again? Thank you. So this is just another view from the other side, which better shows the exhaust gas ducting that would need to be installed to feed the waste heat boiler. Thank you. Next. So the gas turbine driven compressors, this is in summary, are well suited for waste heat recovery and electrical power generation. This will increase the site efficiency by up to 12% compared to the mechanical power that's currently generated for compressing. By generating this electricity as well, we will increase the whole site efficiency. Next, please. And this is up to 4.8 megawatts of free electrical power. This is free power from wasted heat that is currently exhausted from the gas turbines. And this is sufficient for all the existing site load, for the supply of future electrolyzers for hydrogen of up to 3 tons per day, and any surplus can be exported to the grid. And in consideration of National Gas Transmission's other compressor stations, which are all relatively similar with similar gas turbine machines, this waste heat recovery can be quite a straightforward application to apply this to other compressor stations that the UK has. Okay, I think that's it from me. Thank you.
Thanks, Richard. Should be over to Sally from Cardiff now. Thanks.
Thanks, Matthew. Hello, everyone. My name's Sally Hewlett, and I've been doing the modelling work on behalf of Cardiff University. So on the screen, we have a schematic, an overview, if you like, of the proposed cycle. As you can see, the gas turbine is in blue, and from that comes the waste heat, which is currently lost to the environment. So the proposal is to send that to the steam cycle, as Richard was describing, and then the electrical power is generated, which is sent to an electrolyser. Now, 2 different types of electrolyser were modelled, solid oxide electrolyser and proton exchange membrane electrolyser. Now, the solid oxide electrolyser can make use of steam to improve electrolyser efficiency. The oxygen is emitted to the environment, and the hydrogen is fed back to the gas turbine as fuel to replace some of the natural gas need, and in doing so reduces carbon emissions. Okay, next slide, please. So if we could peer inside of the schematic boxes, this is pretty much what we would see. So this is the software simulation model. Just wanted to give you a brief oversight of this, not to dwell on it. So next slide, please. So as Richard was describing, 2 types of gas turbine are modelled, the older 1970s model A20 and the turn of the millennium SGT 400. The A20 is in blue on the graph to the right, and the SGT 400 is in yellow. And each of those gas turbines was modelled with the 2 types of electrolyser previously mentioned. So solid oxide electrolyser, but also the PEM. For the same fuel energy, the SGT 400 produces more hydrogen, leading to greater CO2 reductions. That's not surprising, given that it is a more modern gas turbine and runs more efficiently. At each gas turbine's maximum thermal power, we can see that approximately the same amount of CO2 reduction takes place. So for the solid oxide electrolyser, which is shown in the solid dots, we have about 600 kilograms per hour CO2 reduction for both types of gas turbine, and it's about 500 for the PEM electrolyser. So while they're equivalent at their maximum load, it's not the case for the minimum load, where the SGT 400 produces around twice the CO2 reductions of the older A20. And as we can see, the solid oxide electrolyzers are more efficient than the PEM for hydrogen production, but they do need to be kept warm. And the gas turbines at the compressor sites are used intermittently. So to keep the solid oxide electrolyzer warm, we need to import grid power. And of course, the grid power will have a certain carbon intensity associated, so leading to scope 2 emissions. To negate the scope 2 emissions, a certain number of hours of gas turbine operation will need to take place before we can start realizing CO2 reduction benefits. Of course, if renewables power is used, then the number of hours would be 0. So a solid oxide electrolyzer, the modelling shows, would save, depending on the gas turbine used, 24 to 34 tonnes of CO2 for every 100 hours of typical operation once the scope 2 emissions have been negated. PEM electrolyzers, on the other hand, do not need to be kept warm, so would immediately start to save 20 to 28 tonnes of CO2 for every 100 hours of typical operation. So as you can see, depending on the utilization of the site, the electrolyzer decision will vary, with lower utilization sites favouring PEM electrolyzers. And the number of hours is obviously related to the carbon intensity of imported electricity. Okay, thank you very much. That concludes my overview of the modelling.
Thanks, Sally. That's great. If we can move to the next slide as well, please. So I've more or less just summarised what Richard and Sally have said, but some of the key sort of benefits that we could potentially see here are obviously system efficiency improvements. As soon as you recover that energy that was otherwise lost and do something useful with it, you get a system efficiency gain from your operations, which is very positive. Up to 4.8 megawatts of electricity can be generated, and as we've sort of touched upon, we've been obviously focused on hydrogen production from that electricity. Obviously, if you consider some of the issues that I think the Connectrolyser project was touching on in terms of these large electricity connections, which we are going to start to see more and more of, a project like this where you are, obviously Richard said free electricity more or less, compared to sort of paying as you would normally. It's very sort of beneficial in terms of hydrogen production. Through Sally's modelling, we've sort of seen that we could potentially blend up to 20% by volume of hydrogen at maximum hydrogen production capacity based on the steam available, and that would obviously lead to some a reduction of emissions from the system itself, and I've said there, yeah, it relates to about 8.2% CO2 savings. Again, this relates to kind of the maximum that we could see if you're blending directly. It doesn't consider storage, so if we were to actually store hydrogen that we produce, we could potentially see larger blends and see more emissions reductions as well. I think the use cases, as I touched upon at the beginning as well, electricity generation, obviously power the site, so we're avoiding kind of importing or using electricity from the network, and we can have more of a sort of self-contained site. Potential export of electricity as well. Hydrogen production, which we've talked about a lot, and heat networks as well. So can we use that heat for something on our own site? So for example, fuel gas preheating on the smaller scale, or can we actually find a user of steam that we can connect to? Obviously depends very much on who and what industry is nearby to our sites physically, but I think it just highlights that it's a very sort of flexible solution, and you could do lots of things with it. If we could move on to the next and I think final slide, please. So yeah, just to touch upon the beta phase plans. So a physical demonstration. So we'll go through all of our usual kind of processes in terms of finalizing that detailed design, going through all the planning and consents, environmental permitry, our FPSA safety assessment processes as well, procurement and obviously manufacture of the equipment that we're going to use, getting it on site, putting it all together, commissioning, and then actually testing the system as well would be our aims for the beta phase. Alongside that, we would do more of the system modeling. Like I said, it was very useful, but we can actually now kind of tailor the model to specific sites, and we can look at the capabilities of those and the potentials for those specific sites. Working out the kind of regulatory barriers that might be associated with power export as a sort of gas transporter licensee. There's probably some barriers that we would need to consider there. Further refining the business case as well, relating this to what's going on in our other sort of compressor strategy work. So hydrogen is becoming more and more into the conversation. So it's working out what sites would be the best sites to put this at. Integrating with the hydrogen production and storage, as we've mentioned plenty of times, including relating to our hybrid storage project, which Ellie presented on earlier, that we've very much been kind of collaborating all the way through discovery and alpha so far between these projects, and linking it to our other hydrogen work as well. So Project Union and the hydrogen allocation round works as well, and also linking up with other industry who could potentially use this solution or be a user of the full solution as well. So I think that's everything. So I think we can move to Q&A now. Thank you very much.
Great, thank you. A couple of questions here. This is from Hussein. What is the estimated gas storage capacity in the pipelines in the NTS?
Yeah, I saw this one come in. I was desperately looking for something that I could easily say, yes, here's the number, and I failed. But essentially, considering it from a sort of pressure point of view, you can imagine gas flowing through a network and it just goes from one place to the other. However, the line pack is where we actually boost the pressures using compression, the compressor system that we talked about. So some of our pipelines go up to 94 bar. So that is our kind of way of almost storing natural gas in the network itself. That provides a significant amount of flexibility to GB's energy system, really. So if we have a certain amount of gas that's actually stored in the pipe, we can sort of build that up in anticipation of large kind of demand periods. So when electricity demand might peak, we have a certain amount of gas sort of stored in our system to get ready for that. There's plenty of data that on our website as well, which shows what the kind of line pack is within our network, sort of live as well. So I can link that in the chat perhaps.
Thanks for that. And just one question from an anonymous attendee. How is this project complementary to the other HyNTS projects? So I think just wanting you to highlight any synergies between this project and the other one which was presented on.
Yeah, for sure. So there's obviously a very strong connection. So the hybrid storage system was originally sort of intended to be installed at compressor stations. Obviously, if we're looking to decarbonize our compressor stations with hydrogen, we want to be able to store hydrogen safely. So I think certainly where the hydrogen production and storage was considered, Richard was sharing a lot of information with the hybrid storage alpha team and supporting their modeling work and their sort of use case development as well. In terms of heat recovery, so the solid state hydrogen storage system can actually benefit from heat recovery as well. So the way that the solid state storage works to release the hydrogen is actually heating up the material. So obviously you spend energy to generate that heat, but if we've got it from the compressor station itself, then that's a nice little synergy that we found in that regard. So yes, certainly as a full solution, we could see waste heat recovery coupled to electrolysis with a hybrid hydrogen storage system. So that would be our kind of ultimate goal, if you like.
Dream. Great. Well, I think that actually brings us to the end of our presentations. Thanks very much to everyone who joined today and to all of our presenters as well. We're really looking forward to seeing what's to come for beta. And yeah, just best of luck to all of those who are applying. Please do connect with us if you'd like further information as displayed here. And yeah, we look forward to seeing you in our next show and tell sessions that we've got coming up. Thank you.